Today we have Dr. Kim Lisgo with us to present on the work of the Canadian, the Boreal Ecosystem Analysis for Conservation Network group, presenting on the conservation matrix model and its application in the Northwest Boreal LCC. The Canadian Beacons Project was founded at the University of Alberta in recognition for the need for a made-in-Canada approach for conservation planning in Canada's Boreal region. They are building a credible scientific framework for comprehensive conservation planning through the development and application of leading-edge conservation science that includes consideration of both protected areas and land managed for other values. And the premise of their research is that the ultimate goal of conservation is to identify human activities that are compatible with the maintenance of biological diversity and the integrity of the ecological system. So that's the conceptual scientific framework that guides their research and the development of their conservation matrix model. Kim has studied and coordinated research on the effects of industrial development on the ecology of boreal wildlife, including birds, weasels, flying squirrels, and caribou. And her primary interest is ecologically sustainable resource development and the maintenance of ecological integrity in the boreal system. She has been the project manager and researcher with Beacons for more than 10 years at the University of Alberta, and she is based in Whitehorse, Yukon Territory. And she's the lead conservation analyst for the Canadian Boreal Forest Agreement, or CBFA, and she's involved in leading conservation planning exercises across Canada from British Columbia to Newfoundland. Through the partnership with the CBFA, she's been applying and advancing a lot of the methods that are going to be presented today. So we're very excited to have Kim presenting and talking about the work, bringing the conservation matrix models from Canada and into Alaska. And just to remind everybody to please keep your phones on mute. There will be plenty of time for questions and answers at the end of the presentation. And for those of you in the room here, you make sure that your cell phones are on silent or turned off. And this is part one of a two-part webinar series that Kim will be giving. The topic and level of detail that's included in the next webinar, that's scheduled for the same time on Wednesday, July 8th, will be determined in large part by the questions and feedback that we get from the end of this presentation. So keep that in mind. If there's anything that you would like to know more about, or either any kind of questions that you would like to go further on, she'd be happy to include that into part two of applying the conservation matrix model for the LCC. So with that, I'm going to turn it over to Kim, and we'll get going. And just a note, we will record this. We'll be recording today's presentation, and it will be available on our website shortly. So thanks a lot, Kim, and take over.
Okay, thank you, Amanda. Just a small correction in my bio. While I feel like I may have completed a PhD, I actually have not been. So I'm actually Kim Lisgo, not Dr. Kim Lisgo, but thank you for that. So before we dive into the nuts and bolts of the presentation, I'll introduce you to who the Beacons Project is. So there are a number of universities affiliated with the Canadian Beacons Project. The Beacons Project itself is located at the University of Alberta, where we have Dr. Fiona Schmiglo. On the East Coast, we have Memorial University with Dr. Sean LaRue. At the University of Laval, we have Dr. Steve Cumming, and at Simon Fraser University here on the West Coast, we have Meg Krawchuk. And a number of the Beacons Project members have attended our community call today. So in terms of the work that Beacons has been involved in, this graphic basically gives you a summary of what we have been doing. We've been involved in a number of initiatives. There we go. We've been involved in a number of initiatives across Canada. Amanda mentioned the Canadian Boreal Forest Agreement. That's shown here by the brown areas, where we're working with forest companies and environmental organizations to apply large landscape conservation planning. We've also been involved with a region in Northern Ontario, as well as Quebec, and now we're extending into Alaska with our partnership with the Northwest Boreal LCC. Now, one of the reasons why the Beacons project started up is that within Canada, Boreal region as well as Alaska, we have this incredible opportunity to plan for large impact landscapes, which is really unlike anywhere else or few places in the world. So, given that we were going to start planning on large impact landscapes, we realized that there was an opportunity for a paradigm shift in conservation planning. So, classic conservation planning is really, for the most part, conservation science has dealt with landscapes that already have been highly altered. But in Canada's Boreal as well as Alaska, we had this opportunity to plan in these large impact landscapes. So we could move away from reactive conservation planning towards more proactive conservation planning, which signifies a shift in the paradigm of conservation planning. So we can move away from the classical conservation model, which is asking the question of how much is enough in the context of relying on protected areas for conservation, to moving to a model which I refer to here as the conservation matrix model, where we ask the question, how much is too much? So how much is too much development on the landscape? And so in order to move or shift in this paradigm, we're now starting to look for the major sustainability. So we know that those landscapes that have been highly impacted really have low ecological integrity, where as we move towards the question of how much is too much development on the landscape, we're interested in maintaining high ecological integrity, so maintaining functioning ecological processes within their natural range of variation. So how do we go about identifying what we refer to as this high integrity? So how much development can we actually allow on the landscape? There's a lot of uncertainty associated with asking that kind of question. So what is actually sustainable on the landscape that we need to think about when we're asking this question? So those uncertainties can come from our knowledge of the systems, which is largely incomplete. There's a lot of natural environmental variability across the Boreal region. The responses of these ecosystems to development are largely unknown. Often the threshold, so how much development can you actually allow before an impact on a process occurs, are notoriously difficult to identify. Then there's also social licenses, which can be dynamic depending on the politics of the day. And then we also have climate change, which can compound all of these issues. So when we think about sustainability, identifying sustainability, it really is a grand experiment, and it comes along with all of these uncertainties. And so one of the ways we can directly address uncertainty is through the scientific method. And so in order to apply scientific method on a landscape, we need control. So as a recognition of this, the Beacons brought together both information from the realm of conservation science and also that of resource management to come up with a model that allows us to treat human development on the landscape as an experiment. And this model we refer to as the conservation matrix model. So it's a new framework for thinking about landscape conservation. So the conservation matrix model, or the CMM, is proactive, it's precautionary, and it's comprehensive. And it recognizes the value that all elements of the landscape have towards conservation planning, and that we don't rely solely upon protected areas. So this approach focuses on maintaining landscape processes that support ecological integrity, natural patterns of species in their distribution and abundance, and the ecological function. And what we're trying to do here is we want to, rather than managing for a minimum critical level. So now I'll walk you through the conservation matrix model. So there's a number of elements, and we'll start with the broadest one, which is the conservation matrix itself. So this is the supportive environment that maintains the natural and cultural values across the landscape, and it plays a critical role in maintaining connectivity or the flow of ecological processes across the landscape. And it supports the overall ecological integrity and landscape sustainability. So we start with this as the foundation of the model. The next thing we add to the model is, of course, there's going to be some form of permanent infrastructure in most areas on the landscape, which is signified here, showing the black line. But one of the elements we need for our sustainability experiment is our controls, and those are our ecological benchmarks, which are illustrated here in the darker green areas. So these ecological benchmarks are essential for applying this model. So these serve as the anchors of a conservation network, They represent the ecological diversity of the region. Since they're serving as controls for our matrix, we require that they be representative of them, and they're a key component of adaptive management. So when we think about sustainability as an experiment, what we're really carrying out here is active adaptive management, where we're learning from our mistakes and modifying our practices on the landscape. So here's an illustration of why we need ecological benchmarks as controls within the sustainability experiment. So this is an illustration where the matrix is shown here in brown, and then we have a forest tenure shown here in the blue. And within that forest tenure, we have a fuzzy creature. So as we're undertaking forestry practices, if a decline is noticed in the biodiversity of that tenure, we don't know what that decline is due to. Is it due to the forestry practices, or is it due to something else that may be occurring outside the tenure? If we include a benchmark network in this model, if we see a decline occurring not only in the tenure but also in the benchmark network, then we know that that decline is due to something other than forestry practices. It could, for example, be due to climate change. And then the third scenario is that if we have a decline in the tenure but not in the benchmark network, then we know that that decline is most likely due to forestry and that our practices need to be adapted. So that decline is no longer occurring. The next element that we add to the matrix model are site-specific protected areas. Ecological benchmarks, while they're often large, will not necessarily capture all of the values that we're interested in the landscape. For example, sites that are of cultural importance, rare species or ecosystems, or critical resources such as early open water. So site-specific protected areas play the role of filling in the gaps in those conservation features that we're interested in protecting on our landscape. Next, within the conservation matrix model, we have our active management zones. And these are areas where we have development occurring. So that could be forestry, it could be mining, it could be some form of hydroelectric development. So that's shown here on this map by the brown outline. So this would be an active management zone. And this zone would be managed under the principles of ecological sustainability, and so we would be applying adaptive management within this region, using our ecological benchmarks as the control. Then within this active management zone, we have active management sites, and this is where where the forestry, for example, or mining would actually be taking place, and that development would be incremental in its implementation, and there would be some form of effective monitoring to ensure that the development that's occurring there is not impacting the larger landscape. So the idea behind this model is that we're moving away from an approach where protected area network is relied upon as the primary tool for our conservation planning. So it's an acknowledgement that protected area networks will not address all conservation value. And large-scale processes, including, for example, the movement of wide-ranging species, require that we look beyond protected area boundaries and we think about how we're managing that larger landscape. And so that's where the conservation matrix model recognizes the valuable contribution that all of those landscape elements can play and must play in order for us to achieve conservation and sustainability goals. So it's just a very quick run-through of the conservation matrix model, and so now I'm going to dive into elements of the conservation matrix model, primarily ecological benchmarks, in the context of our partnership with the Northwest Boreal LCC. So in order for the conservation matrix model to work, it requires that adaptive management be a key element. And for that adaptive management to work, we need benchmark networks. So this is a map showing the Northwest Boreal LCC, shown here in the outline in green. It intersects a large portion of Alaska, most of the Yukon Territory in Canada, a portion of the Northwest Territories, and also British Columbia. So as part of the partnership, we're working on designing candidate benchmark networks for the Northwest Boreal LCC. And as part of that, we're incorporating focal species into their design. And in the fall, to initiate the work, we undertook a pilot study for the Bureau of Land Management within two of their planning regions. the Bering Sea Western Interior here, and the Central Yukon shown here in purple. So what I'm going to do first is I'm going to walk you through the principles behind benchmark design, and then I will show you some results or snapshots or a few results that were developed for the Bureau of Land Management pilot study area. So when we're designing ecological benchmarks, there's four primary criteria that we're thinking about. We're thinking about intactness, size, hydrology, and representation. And we think about those four elements in a two-step process. So first we start with the identification of ecological benchmarks. This is based on intactness, size, and hydrology. So we identify potential ecological benchmarks first, and then we bring in representation. So, and we bring in a number of conservation features or biodiversity indicators that we use to assess that representation. And this is a little different than classical protected areas planning, which has usually started off with representation first. So representation is not our goal, rather it's one of the criteria that we use to select the ecological benchmarks that are best suited for our planning region. So we'll start off first with intactness. So intactness, this is what, or intactness, or the absence of human disturbance, this is what we use as a proxy for ecological and evolutionary processes operating within their natural range of variation. So for our benchmark to be effective, we want the things that we're monitoring and learning about to be doing what they're supposed to be doing, operating within their natural range of variation. And one of the ways that we measure intactness on the landscape is the absence of human disturbance. And so we've created a data set for the Northwest Boreal LCC based on two data sources that measure footprints on the landscape. So the first is the Landscape Condition Model of Alaska, which came out of the Alaska Natural Heritage Program. For this portion, so the Alaska portion of the study region, the Northwest Boreal LCC boundary is shown here in black. And then for the Canadian portion of the study area, we're using a data set produced by Global Forest Watch Canada called the Human Access of Canada's Landscape. And as we can see, based on the coloration of the landscape, dark green being 100% intact, down to pink being 0 to 59% intact, then we have a landscape of very high intactness. So there's lots of opportunity here for us to design ecological benchmarks. So after intactness, we start to think about size. And so there's two primary factors that guide the size of ecological benchmarks. The first is that we want them to capture large-scale ecological processes. So these are the large-scale processes that shape the patterns that we see in the landscape, and they operate over very large time frames. And these processes tend to be slower, and they shape the smaller, faster processes that are operating in the landscape. And those smaller, faster processes are the ones that we would most likely be monitoring within our adaptive management program. And we also want our benchmarks to be resilient to natural disturbance. So to incorporate these two elements into the define or the determination of the size of an ecological benchmark, we use methods that were originally developed by Leroux et al. 2007, the graduate student of Fiona at University of Alberta. And we use the methodologies or modifications in those methods to determine what we refer to as the minimum dynamic reserve. And so what do I mean by a minimum dynamic reserve? So a minimum dynamic reserve is the minimum area required to be resilient to natural disturbance, such that internal recolonization for habitat types that are vulnerable to that natural disturbance are maintained within the reserve at all times. So for example, if our disturbance is fire, then those vulnerable habitat types are going to be flammable vegetation types, so forests, for example. If it's something like insect outbreaks, it may be a particular tree species that's a vulnerable habitat type. So we can think of these internal recolonization sources as lifeboats for species that rely on habitats that are vulnerable to natural disturbance. So within our benchmark, we want to make sure that we have these lifeboats at all times. So I'll just illustrate that here. So if we have a reserve or a benchmark that's shown here in purple, and we have a green habitat type here which is vulnerable to disturbance that this bird creature relies on, we want to make sure that if that natural disturbance were to occur, if it happens to be fire, that some of this green habitat or vulnerable habitat would be within the reserve at all times so that our bird creatures would be able to reside within the benchmark and not rely on external sources. for recolonization. Now, to determine the size of minimum dynamic reserves, this is a very high-level overview. We use a dynamic landscape simulation model called CONSERVE. There's a number of inputs that go into this simulation model. There's fire data. There's a fire model associated with CONSERVE, as well as a vegetation succession model. And so we have fire data, a land cover data set, an age data set, as well as succession rules that all feed into this model. And to determine the minimum dynamic reserve, we typically run a time frame of 250 years, and we repeat that simulation 100 times. And through those simulations, where we track the amount of plantable vegetation types within our candidate reserve, and some minimum amount of each of those plantable vegetation types must be maintained within the reserve at all times. If at any point they do not, then the reserve is too small and we need to make it larger. So this is the process that we go through for identifying minimum dynamic reserves, and if it's of interest, this could be a topic that we could expand upon for the next presentation that we're given on July 8th. So this figure shows some examples of minimum dynamic reserve estimates, and this is for the BLM pilot area that I pointed out at the beginning. So we have the boundary of the Northwest Boreal LCC shown here in red. The BLM pilot area is shown by the hash marks here, and in black, first in the colored regions in the back, those are eco-regions, and that's the scale at which we undertake the benchmark analysis and the identification of minimum dynamic reserves. We can see a number, and that's the minimum dynamic reserve, or MDR, that was estimated for that eco-region in square miles. So we have a fair amount of variability in the MDR estimate for the BLM pilot area, from as low as 714 square miles for the Alaska Range up to 6,000 square miles for the Nevada Hills. So this is the size estimate that we use for designing ecological benchmarks in terms of capturing large-scale ecological processes, as well as ensuring that our benchmark is resilient to natural disturbance, maintaining those lifeboats or vulnerable habitat types within the benchmark at all times. So next we're going to move on to the third component of identifying our ecological benchmarks, and that's hydrology. And so there's a number of ways in which we incorporate hydrology into the design of ecological benchmarks. And the first is through the use of catchments as building blocks. And catchments are approximate drainage areas for stream segments. So in this slide here, I'll illustrate how to go about constructing catchments. So this is for an example in Canada. So we have a digital elevation model. On top of that, we put the drainage network, the stream network, and then using GIS software, we're able to identify approximate drainage areas for each of those stream segments, and those are shown here in this illustration by the brown outline. So those are the building blocks that we use for assembling the ecological benchmarks. So we have developed a catchment data set for the Northwest Boreal LCC. Again, as a cross-boundary data set, we have to draw from and harmonize data sets from either side of the border. So for Alaska, we use for the stream network or the hydrology source, we use the National Hydrography data set 1 to 24,000, and on the Canadian side, we use the National Hydro Network 1 to 50,000 for a stream network. And then we bring in two digital elevation models, one for Alaska at 1 to 24,000 and one for Canada at a scale of 1 to 50,000. And this inset here shows you a blow-up of what those catchments look like, with the stream network shown here in blue, and then the catchment boundaries shown here in gray. This box down here, depending on whether you're more imperial inclined or towards metric, shows the sizes of catchments across the Northwest Boreal LCC. So in terms of square miles, the catchments can be as small as 0.19 up to 107 square miles. But the mean is 1.1 with a median of 0.8. So the catchments overall are fairly fall towards the smaller end of the spectrum. So now that we have these catchments as building blocks, we amalgamate them into benchmarks using a software tool called Benchmark Builder. And so benchmark builders construct benchmarks to a user-specified size and intactness and emphasizes headwaters in the benchmark construction. So this figure here, I'll just very briefly illustrate how a benchmark builder goes about constructing a benchmark. So the builder will start from a specific seed, which is a catchment. And the seed catchment in this illustration is labeled 1 and has the red outline here. So in terms of emphasizing headwaters in construction, the first thing the benchmark builder does is it grows upstream. And so it starts with 1, and then it grows upstream and adds these 2 catchments here. Now it's reached the headwaters, so it can't grow upstream anymore, so it immediately starts to grow downstream. So it moves here and adds catchment number 3. Once it's added a catchment downstream, it immediately starts growing upstream again. Once it's reached the headwaters, then it goes downstream again, and then back upstream, and so on, in this fashion. And the builder will continue to do this until it reaches the size or the minimum dynamic reserve that we've specified in the construction process. Now, there are a couple reasons why we emphasize headwaters in benchmark construction. One is for their influence on downstream biodiversity as a primary interface between upland and riparian areas in the overall stream network. And the second is to minimize the vulnerability of the benchmark to upstream disturbances. So this figure here is taken from a paper by Pringle in 2001 and illustrates the location of a reserve on a stream network and how it can be vulnerable to anthropogenic disturbances associated with that network. So, for example, if we place the benchmark, for example, in the headwaters of the stream, there are a number of disturbances that can be occurring downstream, but we don't have to worry about anything coming in to the benchmark. Well, we shouldn't be ignoring these. For example, a dam can impact the migration of species up and down the stream network. We have at least minimized the input of upstream disturbances. If we place the benchmark network here in the middle of the stream network, you can see the vulnerability that may exist for a benchmark both from the upstream direction as well as the downstream. And then if we place it at the most downstream portion of the network, of course it's vulnerable to anything that could be occurring upstream. So by emphasizing the construction of our benchmark network to include headwaters, we're removing that vulnerability from upstream disturbances, as well as capturing the ecological importance of those headwaters within our benchmark. Now, before we go about identifying ecological benchmarks based on our 3 criteria of intactness, size, and hydrology using the builder software that I just described, we always start with existing protected areas first because they can, in many cases, meet these 3 criteria, and we don't need to move on to the builder software to identify them. So this is just a map showing the protected areas network for Alaska and the one that we use with the Bureau of Land Management pilot area, and we'll return to that shortly. So now that we've completed this process and we've identified a suite of candidate benchmark networks for our planning region, the next step then is to assemble those benchmarks into networks that are representative of environmental variation. And we use 4 data sets to represent environmental variation on the landscape. The first is climate moisture index, and this describes the landscape in the context of the difference between precipitation and evapotranspiration. And so this figure, you can see we've got coloration from high to low, with the blue showing as areas that have more precipitation than evaporation, and then low where we have water deficits, where we have more evapotranspiration than precipitation. So these tend to be a drier climate. We have gross primary productivity that describes the productivity of the landscape. We have lake edge density, which describes the amount of riparian area on the landscape. And then finally, we have a land cover data set. We're using the North American land cover data set from 2010. And so these 4 data sets have been compiled for the full extent of the Northwest Boreal LCC. So there's a couple of methods that we use for assessing the representation of benchmark networks. The first is using the similarity metrics, the Kolmogorov-Smirnov and the Bray curve. And the similarity metrics simply compare the distribution of each of these indicators within the benchmark network to the distribution within the planning region. The second approach, and the one that I'm going to highlight today, is an MDR-based target for assessing representation. And so this requires assigning criteria to classes. So land cover obviously comes as we already classify, whereas current moisture index, GPP, and leakage density are continuous indicators that require that we assign them to classes. And so for the work that we do at the Bureau of Land Management, we assign them to 20 equal interval classes. And so using land cover, I'll illustrate how we come up with those MDR-based targets. And so in this example, we're using an MDR of 400 square kilometers. So in this simple example, we have 4 land cover classes. This shows the amount of area for each of those land cover classes within the ecoregion. And this number describes the proportion of the ecoregion that is comprised of that land cover class. So to determine the target, we simply take our MDR 400 square miles and we multiply it by the percentage of that land cover class. So we're essentially determining proportional representation using 400 square kilometers as the total amount. So 12% of 400 square kilometers gives us 50 square miles for both water and wetland. For forests, where forest makes up 50% of the landscape, our target becomes 200 square miles, and for shrub, where it makes up 25% of the landscape, 25% of the MDR is 100 square miles. So a benchmark network is considered representative of the ecoregion if it satisfies the MDR-based area targets for all classes of the eco indicators. Now, within the Bureau of Land Management work, we satisfied those targets across the network, but we've moved towards an approach where we satisfy those targets by reaching them within an individual benchmark network. And this has advantages both for maintaining the resilience of that particular indicator class, as well as properties for monitoring programs. So that's a very quick run through on how we go about designing ecological benchmarks, and now I'll show you some results from the Bureau of Land Management pilot area. So I'm going to focus on just 2 ecoregions. We're going to look at the Lime Hills located here and the Catchment Mountains here in yellow. So we'll start first with the Lime Hills. But before we do that, something that I haven't introduced you to yet is the difference between system and subsystem benchmarks. And within the Bureau of Land Management pilot area, we look at both system and subsystem. So what do I mean by these 2 classifications? So we can think about system and subsystem benchmarks along a gradient of intactness from high to low and a gradient of size from small to large. And when we're designing ecological benchmarks, what we're looking for are these highly intact, large regions, and so that satisfy our minimum dynamic reserve size, and that are highly intact. So all that our processes are operating within their natural range of variation. If we compromise on either the intactness or size, we move into a realm that we refer to as subsystem benchmarks. So the benchmarks, we still have some utility within a monitoring program, but that utility is somewhat restricted, and we're no longer monitoring at the system or the full extent of the ecosystem. We're just monitoring components of it. So within the Bureau of Land Management pilot area, you'll hear me referring to both system and subsystem benchmarks. But what we're really trying to achieve is this gold standard up here. So in the Lime Hills, this figure here illustrates that we have an ecoregion that's highly intact. You'll see these colors repeated for the next ecoregion. So this is the color of the landscape based on how intact those catchments, the building blocks are for the construction of ecological benchmarks, with a dark green being 100%, down to 80% intactness for the lighter green, and then yellow and orange for anything lower than 80%. When we're designing an ecological benchmark, we would ideally like it to be 100% intact, but given historical human activities on the landscape, that may not always be possible. And so for designing a system benchmark, we may at times drop down to a minimum catchment intactness of 80%. So So, as I mentioned, this landscape is highly intact, so there's going to be lots of opportunity for constructing ecological benchmarks here. We also have a very large protected area, Lake Clark National Park, with a high level of protection, which would make an ideal candidate for an ecological benchmark, assuming it meets our criteria of intactness, hydrology, and representation. So before we dive into trying to build something new, the first step we took here in this ecoregion was to evaluate the ability of this protected area to function as a benchmark for the ecoregion. Now, one thing you'll notice here is that the ecoregion is defined by a black line, but I've highlighted a region that extends beyond the ecoregion. When ecoregions were delineated, they did not take into account hydrology. So often the ecoregion boundaries will truncate hydrologic flow. So there'll actually be a river network or stream network crossing that boundary. So to address the artificial barrier to hydrology that the ecoregion boundary may put upon the analysis, we buffered the ecoregion by hydrology unit. So for the Lime Hills and other ecoregions in the BLM pilot area, we buffered the ecoregions by up 12 units in an attempt to remove that artificial barrier to hydrology. So in terms of assessing the benchmark or the protected area, we looked at 4 levels of intactness, minimum catchment intactness, 100, 99, 90, and 80, and you can see by the various shades of purple down to pink identifies areas within the protected area that meet those 4 intactness criteria. As well as and so all of these areas all satisfy a minimum dynamic reserve, so they're system level benchmarks. In addition to evaluating the size and intactness, we also look at how well those benchmarks, or candidate benchmarks within that protected area, capture upstream areas. And so we can see in this figure by the darker blue, areas associated or outside of the protected area that are upstream. And so these dark blue identify areas that are unprotected but upstream of the protected area here. So as a system level benchmark, we know that they exceed the MVR, which is 913 square miles for this particular ecoregion. If we use a 100% intact catchment, the benchmark would be 1.4 times the MVR, so that's the dark purple region here. If we use all catchments greater than 80% intact, the protected area is 2.7 times the minimum dynamic reserve. And the total upstream area associated with benchmark designs in this protected area would be 654 square kilometers. So then we assess the representation of this candidate benchmark network, and for this analysis, I used the benchmark network with a minimum catchment of 80%. That's why you can see I've selected the whole region within the protected area. It's shown here in pink. So that's the system level benchmark that we're evaluating for its intactness. And we're looking at these 4 indicators here. So this table up here tells us the number of gaps that we have in our MDR target. So we're going to focus on benchmark 4 in the end. So this is the benchmark option from this protected area that has a minimum catchment intactness of 80% and has 100% met our MDR value. And so we'll start with land cover here first. There are 13 land cover types in the ecoregion, and there are no gaps within this benchmark. So that means that this benchmark has represents all 13 land cover types. In terms of CMI, recall that we reclassified both CMI, GPP, and LED to 20 equal interval classes. In terms of CMI, there are no gaps, so we've met the representation goals for CMI. For GPP and LED, we have 3 and 2 gaps respectively, but something to be noted is that those gaps are very small. These particular classes that are underrepresented are very rare in the landscape. Regardless, we looked at how we might be able to capture those missing GPP and LED classes in a benchmark network for this particular ecoregion. So one of the first things we did here was look at Well, if we were to protect this upstream area, which would be ideal, so we could minimize the threat of upstream disturbances to our benchmark, could we possibly take up those GPP and LED classes that are missing from our representation? So the largest GPP class that we're missing is the one that's shown here in light green. So and it's scattered all across the landscape. And indeed, a lot of that class falls within the upstream area. So if we were to protect or apply some sort of special management to this blue region, we would be picking up those GPP classes. For LED, there's a small region here, latent density small region here, that's associated with the upstream area. So the upstream catchments are shown in this blow up here with the light gray outline. You can see that these classes, 12 through 15, including 13 and 14 that we're most interested in, would be represented within our benchmark if we were to add this small region to the benchmark itself. So the recommendations for this particular ecoregion is that the protected area that falls here makes a very good benchmark for the ecoregion. To pick up those GPP and LED classes that are missing, we recommend protecting upstream areas that capture those classes, and overall we recommend the protection or special management of upstream areas to minimize the risk of upstream disturbances to the benchmark. The next ecoregion that we'll look at is the Tuscaloosa Mountains. We have a relatively or highly intact landscape with the darkest green being 100%, down to the lighter green being 80%. You can see that there are a fair number of protected areas that intersect this ecoregion. Again, we have the ecoregion shown here in black, and we've included the 12 units that intersect the ecoregion within our analysis to remove that artificial barrier to hydrology that the ecoregion boundary creates. So again, the first thing we started off with was looking at existing protected areas. There's one system level benchmark and one subsystem level benchmark in this ecoregion. So the purple here, or the pink colors, show two potential system level benchmarks that were identified. So if we were to use a minimum of 90% catchment intactness, it would be the darkest pink, and if we drop down to a minimum of 80%, we would pick up these little small pieces within the protected area to add to our benchmark. In terms of a subsystem benchmark, we have one up here farther to the north, indicated by region B. It's 100% intact. In terms of its size, it's about 80% the size of a minimum dynamic reserve, whereas the system benchmark is 1.5 times the size of a minimum dynamic reserve, which is 2,704 square miles. There are upstream areas associated with both of these potential benchmarks. For the system benchmark, here we have an upstream area of roughly 6,700 square miles, and associated with this subsystem benchmark, we have an upstream area of roughly 5,239 square miles. So the next step then is to look at whether or not these existing protected areas are representative of the ecoregion. And so again, we have a table like the one we saw for the Hils. We have our 4 indicators here, and we're going to focus on a network that has a minimum catchment intactness of 80%. So it's shown here. So it will be this full pink region here and this full green region that we see here. And so if we combine both of these potential benchmarks into the network, how well do we do? So for land cover, we're missing 5 of our land cover classes. For CMI, we're missing 15 of 20. So we're only representing 5 CMI classes adequately. For GPP, we're missing 4, but as the asterisk indicates, those are very rare classes on the landscape. So they may have to be picked up by site-specific protected areas, for example, rather than benchmarks. And then for lake edge density, there are no gaps, so we've managed to meet all of our MDR targets. So this figure here, the colors that you see in the back, that's the climate moisture index. So that's showing the indicator that we have the largest number of gaps in, 15 of them. And in terms of this ecoregion, the benchmark or candidate benchmark network is biased towards areas that are drier. So if we look at the coloration of the climate moisture index, anything that is blue are areas that tend to be more wet, so we have more precipitation than evapotranspiration, and then those areas that move here into the darker brown is the opposite, where we tend to move into areas with water deficits. So in order to complete the representation of those 15 CMI classes, we designed an additional benchmark down here in the south to pick up those wet areas. There were two benchmark boundaries proposed, one that's shown by the red outline, and then another shown by the black hatched line. So by adding either one of these benchmark network options, we complete the representation of climate moisture index, and we also pick up some of these rare GPP classes. The second recommendation that we make here is if we were to pick up, so both of these blue areas are areas upstream of our subsystem benchmark. If we were to protect this lighter blue area, we would increase the size of this subsystem benchmark to a system benchmark, which is ideally what we would like. And we would also pick up the land cover classes where we have representation gaps up here. So the inclusion of this upstream area into our benchmark through some form of protection would complete the representation of land cover and give us a system benchmark rather than subsystem benchmark. So we would have resilience to natural disturbance regimes. We would still have a region associated with the subsystem benchmark with an upstream area that introduces vulnerability to the equation, and ideally that upstream area would be under some form of special management or even protection. Not illustrated on this figure that if you recall from the last one, the system benchmark here also has a large upstream area that falls right about here, and that ideally would also be under some form of special management to ensure that any activities going on within that area would not be impacting the ecological integrity of the system benchmark. So those are examples of the types of analysis that we've done for the Bureau of Land Management and the type of analysis that we'll be doing at a broader extent across the Northwest Boreal LCC. There are other pieces of information that we can bring into designing our benchmarks and protected areas, and that's focal species. So that's the second component that we're bringing into our work with the Northwest Boreal LCC. So through that agreement, the idea is to not only use these core scale indicators that we've been using for benchmark design, but also to bring in finer conservation targets. So those are their focal species. And so there are 5 components to the work that we've been doing with the Northwest Boreal LCC. The first was to identify a suite of focal species, which I'll share with you in just a moment. The second was to identify existing conservation goals and objectives, measurable objectives that exist for these focal species across the Northwest Boreal LCC. Because ideally what we would like to do when we're designing our benchmark network is to also provide benchmarks that allow managers, governments, etc., to use those benchmarks towards achieving their conservation goals and targets. The third objective is to identify data for focal species that exist across the Northwest Boreal LCC. The fourth is then to identify gaps. So where do we actually have, for which of these species do we have gaps in our knowledge? Where do we need more data, and could there be opportunities for us to develop some data sets that would allow us to integrate those focal species directly into our planning? And then finally, the last objective is to use that focal species data that we do have, informed by the conservation goals and measurable objectives that other agencies have for those focal species, and incorporate that into identifying priority sites or the ranking of benchmark network options across the Northwest Boreal LCC. So there's a number of ways in which we can incorporate, first we'll start with the focal species list. So we have caribou, moose, dolphin horned sheep, beaver, rusty blackbird, Old forest-gilled, so that's a suite of 5 species. Lesser scoff, white-winged scoter, shepherd swan, and then 3 fish species. So now I'll just show very briefly some examples of how we could go about incorporating focal species into the benchmarking process. And this is not exhaustive, just providing you with an illustration. Again, if this is something that's interesting to go into more detail at the next presentation. So the first is around the resilience of the benchmark network. So I talked about minimum dynamic reserves. When we're designing minimum dynamic reserves, we can bring in species information to inform the minimum amount of any habitat types that we would like to ensure is maintained within our benchmark at all times. Right now, the minimum amount that we use is very conservative, but we could use species information to inform that minimum amount. Second, we can incorporate species habitat models directly into that conserved software that I told you about. So once we design an ecological benchmark, we can put that benchmark, or the ecological benchmark network, we can put that benchmark network into conserve, and we can track the amount of, for example, caribou habitat that's maintained within that benchmark network at all times. And so depending on what our monitoring program is, for example, we can ask, does that network maintain the sufficient amount of habitat that we need for that monitoring program at all times? That's just an illustration of one way that we could go about doing that. The second is actually to assess the benchmark network based on how much habitat for a particular species they may capture. So this is, again, using the example of caribou. So we have a planning region that's shown here in gray, and we have 3 benchmark networks. And each benchmark network is comprised of 3 benchmarks. And so we have benchmark network here 1 shown with red, benchmark network 2 shown here with orange, and then benchmark network 3 shown here in purple. And so the idea here is that while all 3 of these networks do equally well with regards to representing environmental variation, so that would be our climate moisture index, gross primary productivity, leakage density, and land cover, can we rank them based on how well they capture caribou habitat as well? And so this is just a simple GIS overlay. The caribou habitat here is shown here in blue, and we just simply tabulate the amount of caribou habitat within each of those benchmark networks, and then we can rank them based on that. So based on this particular example, benchmark number 3 here would be our top choice for a benchmark network, given that it also achieves goals that we may have had for caribou habitat. And then the final example that I'll share with you is around climate change, and this is data that's been developed out of the Boreal Avian Modeling Project at the University of Alberta. And using various climate change models, they've mapped out refugia and regions of habitat loss and gain for a number of species across Canada's Boreal region, including Alaska. And so in this example here, for example, we can see refugia is shown in dark green. So when designing a benchmark network or selecting one from a suite of benchmark network options, there are advantages to including refugia so that we know that we have habitat for that particular species at all times, but then also recognizing where habitat will be gained so that we can ensure that we continue to have habitat for that species through time. So again, similar to the caribou habitat example previously, we can do this with the same GIS overlay, so the benchmark networks, and then rank them based on how well they capture each of these habitat types. So let me wrap it up there because I think I'm almost at the end of my time here. So Amanda, I'll pass it over to you.
Great, thanks, Kim. That was a really thorough overview of all the work that you guys have been up to, and just to imagine that you haven't been doing that for that long, so you've been extraordinarily productive. And thanks to all the people on the team for just your willingness to partner with the LCC and your enthusiasm to bring Alaska into that larger context of the Canadian Boreal.